Yeah. So yeah. So the panel discussion will have Rob and Georgia, Jeanette, and Katerina. We originally planned to also have Lawson as a backup panelist, but we have enough panelists, so we will just
instead of
okay.
answer them.
Yeah, so Lawson will also act as a moderator because he's also organizer. So yeah, so let me start with some general questions, and for audience, feel free to jump in to ask. And for online audience, just feel free to post on Zoom and also the website. Yeah, so I think the first question is, we know now is that like it's a era of large foundation models, and people have been trying to scale up data to make like to include all different types of uh like different domains, different maybe also consider different data augmentation methods. So how do you uh like what kind of structures do you think that's still critical to robotics in the next few years? Like just scaling up data won't be able to solve. Yeah. So feel free to.
I think there's probably not a lot of force data out there. Like, if you want to change a tire, how much you need to torque the nuts. If you're gonna hammer, how much you need to hammer if you're gonna chop wood. So I think that force data is probably, there's a lot of pictures of cats and videos, things, but not a lot of the tactile information. So that needs to be all.
Yeah, I was also thinking about physics. This would be probably something interesting to consider of how we come to this problem. I don't think it's possible without interacting. So I am pro collecting experiences, not convinced about the massive way of collecting data and how this would help us generalize. And humans, we are very, very good in quickly adapting to new objects. So we do very fast inferences about like a new heavy object that we have to lift. Of course, given the capacity that you have to lift something, but you will adapt your strategy to make it work. I don't know how we can go around this with the current settings.
Yeah, maybe I have a bias, which is actually if you did have enough data, I think a numerical could solve it. Right? Like if there was enough data, big data, then I actually think the of good architecture could actually solve it. I doubt that we can actually collect enough because it's an insane amount of data that we need to cover the space of all of these tasks that we want a generalist robot to do. For example, for manipulation tasks, we need data. How do you get that? Can you simulate that? I don't know. I don't know about that. Yeah. So with what sensor exactly? So I think actually, if you had enough data, current architectures could probably learn something, but I don't think we will be able to do that. So we do need these priors to become more efficient and leverage the data that we can collect in a reasonable amount of time. And beyond adding priors, I also think we need better methods that actually can basically very quickly adapt whatever the current policy is they learn on data. So, yeah. Now, what these priors are, that's maybe a good question. I think we all totally agree on it. Because it's like a very basic prior. Make a lot of assumptions, and yet you can still even so. For example, in our work, we also used the variance, but we did use it with the formal objects. actually. So, you know, even though the secularies cannot capture everything, it doesn't matter. It still helps even if it's the vulnerable cases.
So instead of answering, can I ask?
Sure.
Okay, I was interested in Jeanette's, the bitter lesson, comment. So if Jeanette could repeat the bitter lesson, because I don't know exactly what it is, then if folks could respond.
Sure, this is not from me. Right? Okay, so for those of you who are not familiar with the bitter lessons, it's an essay from Rich, I guess we could say, maybe. And his argument in a nutshell is basically all of us, you know, any field, also vision and NLP, we have been tinkering around with architecture models that often started off with encoding priors, basically, and certain structures into our models to gain like data efficiency and so on, but from small data. But in the end, the bitter lesson is that all that beautiful thinking and math was actually beaten by just collecting more data and using actually a very simple model instead. And I recommend definitely everyone to read that essay. It's not very long. Think about it, what you think about it.
Yeah, so I guess like when you said that, maybe the reason I asked is because I wanted to answer the question. So language model, VLMs, that's the big thing that well, you know, literally and figuratively. But it does not seem to satisfy Rich's, you know, it's big data, but it's certainly not simple. There's a ton of structure there. It seems like, if anything, that seems in the wrong direction. That's like a huge complexity. I don't know, like, do we see it that way? And then on the other hand, so we got a lot of complexity in the model. On for the LM, there's a lot of complexity in the model and large data, and then for these like you know, equivariant models, with small amount of data, but still a lot of complexity in the model. It seems like neither, you know, is there a place for riches in the world right now where riches simple thing gets satisfied?
Yeah, so I agree with you on the architecture. Now we have it and everyone sort of knows how to use it. So maybe that's why it's supposedly simple. But
And I also don't think that the transformer is necessarily the simple architecture. I mean, it has some simple, well understood now structure. But I also wonder pretty often if it is the right architecture or the way something else will come. It will be more efficient. Many. That would be the next one for sure. I don't know. I think that I don't know if reaches like perhaps comes from the fact that like a universal function estimator that like an infinite NP will capture everything and so on. But maybe like the transformer now that bypasses some things with making like all these kind of correlations in the data. But I also concern like language models in particular is like we have seen that they've been trained to a very, very, very big data set. Language is pretty structured. It has certain rules. They perform well, I assume, within distribution, but whenever the task that you give them becomes way more difficult, they hallucinate. The problem becomes more difficult to really control, even with prompting, which requires a lot of engineering that I don't want to do, for example. So I'm really wondering if we will ever go to the point of having this perfect model, even with language data, and it doesn't seem to be the case. But what I enjoy is the representations that they give us now. I enjoy that we have now these latent spaces of images and language that we can do something with them that we didn't do before when we have one hot encoding, for example. Yeah. So I don't know if Katerina also has like a point with that.
Yeah, so I completely agree with what you guys said. Maybe one comment I always like to think about the autonomous vehicles. So we see the latest Tesla system is end-to-end trained from imitation. They have insane amount of data because they collect their own data because they have their car fleet. Apparently, this new incredible system runs 98% of the time and doesn't even go to 3D. It goes from perspective images to actions. This is what I hear. However, at 2% of the time when you're out of the training distribution that Georgia said, the other system that does 3D, detects all the objects, forecasts where they go, plans and things and so on, kicks in. And so I think of them as system 1 and system 2. So the system 1 can have any architecture, super naive, because it has done the task many times. System 2 needs to have all these inductive biases, abstractions, and so on. It may take longer time to come up with a solution and will essentially give the supervision to system 1. So what now is difficult and out of distribution, tomorrow may be inside the distribution. So maybe, so this is how sometimes I think about it. Thank you.
I agree with the spirit of the good lesson in that hundreds of years of development of sophisticated mathematics and science. And things like AlphaFold can come through the protein folding better than the best biophysicists. So the scientific principles, the furthering of the scientific understanding becomes less relevant when the goal is a success rather than human understanding. So, and that's certainly true with, you know, all of the LLMs, and because they're trained on vast amounts of text and data, and they do very well in that regard. But the issue of other things where there isn't vast amounts of data, then now there is a paradigm where we can get vast amounts of data, which is big companies, you know, OpenAI or whatever, they can employ people to hammer things and measure forces and, you know, and then, you know, then it'll be there. But yeah, I think the sophisticated models, if they don't work as well as simpler ones with big data, then that's the evolution.
I wanted to maybe return to an earlier point and also the intervening question there. Like, so back to the thing about like kind of having background data or some other data that, you know, that doesn't normally kind of come around. I guess one thing I was wondering is, you know, even now, like we're gonna do sensors, etc. Like we're always going to get like kind of slightly different data that you've never seen in your data set. I think this is, at least for in robotics, we're still seeing a lot of that. One impression I get from a lot of the sessions and you know, a lot of the work in some way or another, how do you find things? You're kind of validating, transforming it to a representation that just like exists more frequently in other books, right? Or it has more structure to it. Poses like the twists. You know, we understand these things, and like we can try to write down our whatever we extract in the image into that kind of representation. Would that be a kind of a data sharing kind of mechanism, or is that basically like kind of to what we're kind of sort of.
So I was a little confused on what you said.
Oh,
So specifically on the point, it sounds like you're saying you're going to be talking about like. I was confused by what you were saying. It sounded like you were saying this transfer between, so there's big data sets and which big learning is actually possible, but then there's all these smaller bookings like Foursquare information. So the standard approach is to transfer. Is that what you're getting? What the state? Okay.
so maybe, okay, right? Maybe right in the this is not the best example, right? But like, let's say in the case of forces and you're interacting with objects, like maybe you're using that like, you know, mechanism dependent kind of sensor data to first like figure out, okay, well, what is my kind of the the pose of the object that I'm actually interacting with, and then like now I can rely on kind of pre-trained models to try to predict what kind of future poses. What's that?
Using, say, tactile sensors that are not inside, let's say, the foundation model inputs to extract something about the pose of the object, and then after you have the pose of the object, to somehow use this information inside the pre-trained foundation model to do a downstream task.
Like basically have a more kind of universal, decide like we like, or IEEE or whatever, decide on a more universal kind of standard of data for robotics, right?
Oh,
We-
should
we
we
map-
represent?
Yeah, yeah. We map all of the things to do.
Okay, I didn't understand. Okay, so like saying, we'll take all the data to the point clouds, for example, like featureize point clouds.
Right.
Sorry, what, how was, I don't think this thing would help in particular because.
I think with the fact that, what I think it would help with is that, what I think it would help with is that we, you know, we wouldn't be limited to the small amount of data specific to us with like a particular robot, or a particular system.
And there's maybe what 10,000 robots working compared to billions of people putting stuff on the internet. So I think the amount of data would still be small if it's only our community contributing with us.
Yeah, it sounds a little bit, you're going to the Oxy data set where this was tried, right? So it scales the data up a little bit if you pool them, but you run into different challenges as well. Okay, I'm gonna cite Tucson said something a month ago at a summer school that really resonated with me. He said, like, right now, there's a lot of papers out there that are in the spirit of it works. And I think the reason why I'm thinking about this is because you said something about understanding that it's important for us to actually not just increase success rate, but actually introspect and see why something works. This is at least kind of answer from your comment. I think that it's definitely somewhat the role of academia in works that people who stay in academia are intrinsically driven to actually understand why something works, the underlying principle is behind something. And I think collecting data helps, right? Like it helps us think, oh, okay, it's actually possible. There is a function somewhere, right, that can learn this relationship that we're interested in, and that we also have us as an example for its logical systems. But I think there's still so much work in actually understanding what's going on, because just as an example, if we go for these large models from this infinite data, we have the problem that these are incredibly inefficient. Brain just needs 20 watts, actually, right? So what's the secret behind these 20 watts that we need? That's a really interesting question that we're to actually intersect somehow, I think. Yeah.
Next question.
That's what Janet said, because I also am very interested into that, like, how can we be so efficient? But there are indications that our years of evolution have endowed our genes to read information, but definitely the structure of our neural network helps us learn very fast with not so many data. So this is why I was saying before when you asked me about the reaches, also the bigger lessons, that I think that some things will help, like the representations, but what do you do after that? Like it's like some knowledge representation or whatever we want to call it. What comes after this? Like to come back to this, I don't think we can have a universal sensory representation for data, because I don't think this would be necessarily useful. I want to have the algorithm that can reason of which part of the sensor input, and if I have the sensor, can really help me work. Because if you think about different animals or among us, there are people that survive, for example, by not seeing or not hearing, but they can really be, active and do things and so on. So I also want this for my system because I want my system to also be robust, not only be generalized and general purpose, but I want it also to be robust to different disturbances. And one of the disturbances that will be pretty common about robots will be one sensor to turn off. Right. So, yeah, I don't think it applies there.
So, since we're on, we don't want to, have time so that we make sure that we can go to the reception as well. But I was wondering if the audience has any, any burning question. Go for it, please.
So I'm wondering as far as their
As far as the better letter question, less than question is like there's structure that exists in the problem, like for sure, kind of like what Rob was saying about if your two function lives in this set, like that's what like there's no way you can lose by incorporating that. But then there's also like structure that you kind of approximate, and I feel like maybe that's an aspect of what we're talking about with the bitter lesson. Do you feel like that's a dimension that is meaningful?
Yeah, I totally agree. I mean, I think like the history of robotics is models that don't match things go wrong. So I think like it's typical that there's a mismatch. Yeah. So we need learning for the things we don't know how to. We don't use.
AKA friction.
I also agree.
I agree, and also when it's good, I think we should use it. So not throw away the models just because we can do it without them.
Because
And that's the purpose of science is to understand.
Oh.
Yes, thank you very much for organizing this, what I want to say.
All right. I have like the answer can be short, but a question I have is how do you envision the role of like adding structures to like networks? And how do you envision this evolve in the next maybe 2 to 5 years? Like will more people using this or will less people using this? Like we'll have more compute, more data, but how do you think about like the structure? Like it can be short.
Would you like me to start on this question? This is a beautiful question. Yeah, so I'm very optimistic. I very much believe that people are going to realize the importance of abstraction, visual abstractions, and fine-grained perception will do great and is doing better and better all the time. We'll be able to infer very, very fine-grained object poses, parts, tracklets of those things in videos. I mean, people have started caring a lot about fine-grained 3D tracking, for example, from video. And that's why I'm very optimistic for the future of manipulation, because I think people are going to squeeze out whatever is from behavioral cloning. Then we'll see that, this doesn't actually generalize, and we need to go to more, constraints and rewards we're trying to optimize and how we can combine them through, intelligent planning architectures to get the solution. And once you get the solution, you can distill it to whatever end-to-end architecture you like. But in general, I very much believe on structure for a system 2 type of processing, like reasoning and so on.
I agreed with everything what Katarina said, and I also think at the very least, all the things we know about robotics are useful to generate data, like for example, simulation.
Yeah, Katarina, I just want to make sure I understood what you're saying. So what I heard was that perception models will get better at perceiving fine-grained geometry, and therefore we will be able to use stronger geometric products. Is that what you were saying?
No, I can make it very concrete. Much like the autonomous vehicles generate their own data through planning, they estimate where their cars are, their poses, where they go next, their future trajectories. They try not to go on sidewalk. They have very fine-grained perception through large-scale annotations for all of those things that they can plan without any training data. They just plan and generate the solution, safe solution. I believe we're going to be able to do exactly the same for robot manipulators without large-scale human annotations, because now we know in computer vision how to generate pseudo annotations or how to use multiple views to supervise each other and so on. So I do believe that we're going to be able to have planners to generate manipulation solutions that will distinct in learning models.
Okay, so I'm sorry. So the thing, yeah, the thing that you're saying that we're going to get the geometry and via better perception models, and therefore we will be able to do really good planning, and then we can distill the planner or whatever.
Right, and I do believe the planning architecture also is going to become better by like inverse reinforcement learning. Instead of cloning actions, we'll see the demonstration, infer the constraints, and plan under those constraints and rewards to, generalize them in a very, very nice and, in a way that can go much beyond the training context that this demonstration was given.
So planning is tough because there's a lot of uncertainty with the friction, geometry, like the contact. There's usually occlusion.
Oh yes, well, sure, I totally, but I very much believe on these what we call world models from video. I think we'll be able to find the right representations to be able to predict how the video is going to change, not in pixel space with video models, but in more abstract space in this type of, where the object part is going to go, how it's, it's going to change its state and so on. So it's going to be a learning-based, essentially, simulator that will look ahead, not a physics engine potentially, yes. I mean, this is we're just doing bets for the future, right? So it doesn't need to exist nowadays. The question is about the next 3 years.
Yeah, I think there is a large role for these kind of model-based or learned or not approaches. So these kind of planning-based approaches, but I think they won't help with everything. I think we will need very fast feedback-based systems, model-free systems, basically. So I'm really traditional. I believe in some sort of hierarchy, but then hierarchical kind of reasoning, but also very dynamic. This is what I would like to have ideally. So I would like to have some sort of reasoning layer that it is this what Katarina said, system 1, system 2. I don't know if there are 2 systems only, or if it's more complicated. But I think for one part that we don't take into account currently is not only about the geometry, but it is about the uncertainty and how we can represent the uncertainties. Because I strongly believe that when you are very confident, when you have experienced something over and over again, probably you are model free. You can do it very fast, or you have learned to do it very fast from experience, however this has come. But when you are not sure about something, you usually plan your action according to some model that you have created. I don't know if this will be a vision model, though. I don't believe. Vision models cannot capture necessarily physics. It could give us an idea about like intuitive things, which means this is a more high level of reasoning. But then if you want to learn very difficult manipulation tasks from scratch, it becomes very, very difficult to really say that I will really learn the model and the frictions, etc. And how would this generalize? This is why model-free approaches are more suitable there. So I think it's way more complicated. And I think that we need to understand the different levels of abstractions and representations. Like at the beginning of my talk, I was saying like humans have 2 different ways of representing the world. One that it is a bit more topological, and it's like your rough understanding, like a map.
that you have, it's one part of your cortex, and then there is the other part that it is the geometric features that get activated whenever you want to interact with a very specific part of the scene. And I don't think we are currently investigating this thoroughly, but I think in the future it could be what we are investigating. And cool, and it says there that pre-trained models also fit, in my opinion.
So I think looking at animals, like when a horse is born, and then with a nudge stands up and is walking around and then galloping within a week, there is a lot that's hard-coded models in them. And looking at my own children and their babies, they didn't have models of the world, I think, but they did have a kind of model of self. I'm hungry, I'm uncomfortable, whatever. And there's a multimodal learning process of put that in, what does that taste like? What does that feel like? And I think that's lacking in robotics. It's sort of what we're focused on is performance. Faster than that one, more accurate than that one. Can I do this task better? It's task-based, but the intelligence in humans, and I think comes from play, not from being targeted toward a task. I think that's missing in the community. And everybody's looking at robots that can play, for example. Or
I would say there are like cognitive robotics, for example, let's say, but they're not. This is only an element-based conference. Alvin tells us that in some sense it's a kind of like random play, random interactions. I agree. I started with it like with cognitive scientists in our University of Amsterdam, but it seems like we use play the early stages of our learning process to build an understanding of the world, but then we become goal-oriented because you learn to how to write. They show you, and the goal, like you go into a system that is a school where there is a goal, which is like to get some grade or whatever, to learn something which is a bit more goal oriented. And then there is this other hidden thing that's called intrinsic motivation. What exactly works inside of us that keep us motivated to achieve goals, for example. Yeah, I think play data help a lot in shaping presentations and models in the early stages.
Yes, I believe we should wrap it here. I was gonna say, like, speaking of RSS, is that, if we give up on structure, we'll have solved the problem of like not having enough time to present anything because there's only one kind of paper here. So we don't need to be here for solve. But anyway, back to you.
Okay. Yeah, so then we can end here. It's already 6:12. So yeah, thanks everyone for coming, and thanks to our speakers and the panelists. And also, yeah, Greg, like our speakers, Greg, Rob, Georgia, and Katerina, and the panelists Lawson and Jeanette, and also our organizer. Oh, sorry if I pronounce it incorrectly. Yeah, so yeah, and all the organizers, Elon is not here now, and Julian, and also Dan from Northeastern, and Anchili from NVIDIA, and Cynthia from Numish, and Lawson here. Robin Waters from Northeastern, and Byron Woods from the University of Washington.
Thank you very much.
Sorry, yeah.
Thanks, everyone.